Hello, Professor 博。
嗨，Hello，Professor 唐。嗨
哎，Hello, Professor Andrew Schaff.
Hello, nice to meet you.
Hello. Can we start?
Yes, I'm ready.
Okay. Hello, everyone. I'm Keke Tang from Guangzhou University. It is my great honor to chair a session of AsiaGraphics. Today, we have invited two world-leading researchers. The one is Professor Andrew Schaff from Benghazi University, Israel, and the other one is Professor Hongbo Bo from Harbin Institute of Technology, Weihai, China. Uh, Professor Andrew Schaff is an associate professor in the computer science department at Benghazi University. He has previously served as a visiting associate professor at the Shenzhen Institute of Advanced Technology of the Chinese Academy of Sciences and as a postdoctoral researcher at the School of Computer Science at UC Davis, USA. In 2012, Schaff received the AsiaGraphics Young Researcher Award for his contributions to 3D point cars and related problems. He leads the Lab of Visual Computing and Computer Graphics at Benghazi University and heads the Computer Games track in the Computer Science Department. His research interests encompass a wide range of cutting-edge topics in computer graphics, geometry processing, interactive techniques, and 3D modeling. He is also deeply involved in the development and application of deep learning algorithms to these areas, pushing the boundary of what is possible in visual computing. Through his work, he aims to create groundbreaking methods and tools that enhance our ability to process and understand complex visual data. His talk is entitled "Recent Results from the Visual Computing and Computer Graphics Lab at Benghazi University." Then let's welcome Professor Andrew Schaff's lecture.
Thank you for the nice welcome, and I'm very happy to be here and to talk. Just tell me how long should be the talk, please?
Okay, you can share your slides.
Yeah, what's the time limit?
About 45 with QA.
Okay, great. Thank you. So I'll just plan like this. Okay.
Okay.
All right. So thank you very much for inviting me to your seminar. And when I was asked to give a talk, I thought the best way is to just give you in this time some taste of what's our lab doing, and to give you some maybe a little bit brief of the topics that we're dealing with in our lab. Let me just fix my screen. 1 second. One second. Okay. That's it. Sorry. Okay, I'm sorry. So I'll just go ahead. I will talk about a few works that have been performed in my lab by students that do graduate studies. Most of the work is interdisciplinary, so it's combining several fields and trying to bring some visual processing and computation to other domains, trying again to push the limits of visual computing and deep learning and computer graphics to other domains, and other data. So most of the focus of my talk will be actually on the data modeling, and the part of deep learning and geometry processing would be just the outcome of this examination and analysis. The first work I want to show you is involving a collaboration with the archaeological department, where we tried to perform some kind of reconstruction and filtering to archaeological artifacts. And we call the paper Deep Segmentation of Corrupted Archaeological Artifacts. The idea was that many times in archaeology, where you go and capture some data, the data is heavily deteriorated. And just to take the, yeah. So it's hardly you can see anything, any details. So many times there are humans involved in the loop, and the humans try to figure out what they can see. And of course, it requires a lot of labor, manual and human labor. And not only that it costs time, it's also very long. So we thought about how can we incorporate deep learning neural networks in order to boost this process, to help archaeologists in this processing of archaeological artifacts. Here you can see, for example, a photograph of a stone, and on this stone you see there's a drawing, an ancient drawing, and maybe if we use some kind of knowledge of learning process, we help by providing some kind of segmentation Of course, the segmentation is not 100% accurate because the data is very, very noisy, but it can help in the process. So we came with a network, which I will show shortly. Let me just go back a little in this story and tell you what this all archaeology about. 1 second. Okay, so archaeology involves in looking at visual information. Either it is drawings on stones, it's called petroglyphs, or it can be also drawings and letters that is written on some kind of papers, which is called palimpsests. And these drawings are very, very deteriorated. They're corrupted. They are corrupted either by nature. Yeah, so for example, storms, environment, and etc. deteriorates and corrupts this information, or by other people coming and painting over these findings and etc. And the problem is that we want to restore, we want to reconstruct the original information. Okay, so the goal is to come up with a correct, we call it a deep segmentation, that brings back the original information in form of a mask. This data is found in nature. It's raw data. It's not synthetic, as you can see here. We take some kind of hand-drawn wall art or drawing. You can see the two kinds of drawings here, two kinds of letters, one in Hebrew, one in Arabic, and we want to restore the information. If we focus down, if we zoom to more local places, it's hard to see what's there. You can see it's very hard even for human to find what is the correct mask. So we say that this data is very challenging. So if we use a lot of knowledge from previous analysis of humans, then we can make a neural network learn from previous information and to come up with predictions. And this is what we call deep segmentation. Yeah, our idea is to have some inputs in ancient walls or handwritten letters, and to bring from the noise the correct foreground mask. The mask is not accurate. It's not and it should not be, because there's a lot of noise, a lot of occlusions, a lot of corruption. But it should combine together two sources of information. One is the visual information, some hints of what's going on here. Yeah, we have some hints here and also here. And another information is the knowledge, is the previous data that the network saw, and based on this knowledge, it should boost the mask prediction. What's the architecture that we use? It's quite elaborate. A simple segmentation algorithm, a simple segmentation network was not sufficient here because the data is really too noisy. So we start with a simple unit standard that comes with some initial segmentation mask. But as you can see, this is either too blurry, it lacks some details like the ears and etc., the legs. So we combine it with two additional branches. One is a classifier that tries to help the mask to fit into some kind of known class of objects, shapes. And another branch here, the second branch is a GAN branch. It's an adversarial network that tries to make these predictions look realistic. I will talk a bit about these branches and the network. So the initial unit is an encoder decoder, quite classical. It has three losses. One is a binary cross entropy that tries to separate between different classes. So the classes here is the foreground, which would be white, and the background, which should be black. So we have here the foreground background classical problem, but then we have also additional losses that try to regularize and improve the prediction ones and total variation, trying to make it into one mask so we don't have disconnected components. And another one is a regularization, which tries to make it unblurry, tries to make it a sharp black and white mask. Okay, the second part is a classifier, which has which is also it's also a classifier which tries to add some knowledge to the shape. So basically, what the classifier tries to do, it tries to say, I want a good enough mask so that I can say what class does it belong. So in a way, it tries to boost the prediction of the foreground background segmentation into known shapes. So it's not enough to give here a mask. The mask should be good in terms of its classification. So we have here classes, and I will talk about the classes soon. And we have here a class cross entropy loss, which we add to the overall loss of the network. The second branch here is a GAN. And the GAN is simply trying to look at a mask, the predicted mask. As you can see, this is the mask of the unit of the encoder-decoder, and tries to make it look realistic. Realistic means that it sees a lot of true masks, ground truth masks, and predicted masks, and the discriminator should say whether it's a true mask or a synthetic one. If it's a true mask, a mask that was made by a human, then it's good. If it discriminates between a synthetic mask that was predicted by the unit, then it's bad. So this is like an adversarial game that tries to boost the unit to make the masks look more and more realistic and more like it was made by a human, and not something that is an encoder-decoder output. It's not enough. We had to add some kind of augmentation. So one kind of augmentation was trying to add some noise to allow the GAN to generate better examples. So here, this is the unit output. Here is an animal, here is a person, and we simply cover some parts of the shapes, and the GAN is able to reconstruct it this way. We boost the GAN convergence. The data set that we got is obtaining pairs of inputs. Here, there's a petroglyphs inputs and the masks that were created by humans. And same was the palimpsest, the handwriting dataset, where we have these inputs that are heavily corrupted and letters on letters and so on, and the true ground truth that is covered here. The data is very small, and we had to augment it. So the augmentation here included separation between the foreground ground truth and the background, and creating candidates of foregrounds, as you can see here, foreground paintings and backgrounds that then we blended together. So we take like photographs of walls together with photographs of petroglyphs of hand-drawn animals and the persons, and we blend them together, the background and the foreground, to generate new and more inputs. For the palimpsests, it was harder because here we have not only one foreground and one background, we have here several foregrounds. We have several handwritten symbols that we need to separate. So we have three separations. One is the original, the initial letters that we try to reconstruct. Then we have some letters that are not needed, that we're not interested about, and the background. So we do a context-aware in painting, where we fill the background and the occluders, and also we do in painting in the foreground to have a smooth foreground, which then we can paint. So we have three layers: a background, some occluders, and the foreground, where we can paint together through some weighted blending to generate new data. So this is a very important step because it allowed us to come from very small data set. Here we start with 80, 10, in the hundreds of ground truth artifacts, both for the petroglyphs and the palimpsests, not more than hundreds. And we were able to get to thousands, nearly 10,000 in the petroglyphs and nearly 20,000 in the palimpsests, which is something that the networks could work with. And here you can see results of our reconstruction. So this is almost nearly invisible inputs. And here are the masks that we were able to predict. And it makes sense. It helps a lot to give an initial guess what's here. So this is for palimpsests. You can see there are several animals and persons with weapons. And same for the handwritten symbols. You can see this heavily occluded, heavily corrupted, and we're able to reconstruct the full shape of the symbol. We try to evaluate also quantitatively the results. So we look at several metrics, binary and the MSE, and the mean intersection over union, and F1, and the earth moving distance. And we can see that when we run our model on our data, we are almost as running on standard segmentation problems like COCO. You can see, of course, our data, since it's much more corrupted and noisy, it's below COCO, but not far away in all metrics. So this is quite a good result. We also ran some empirical user studies in order to see how useful our segmentation is. And of course, this is not a segmentation that always it's something that archaeologists or professionals are happy about. So in the majority of the evaluation, they said that the quality is good, is above negligible, and also the efficiency of helping in processing this data is quite good. We also did a more extensive user study evaluation where we gave we gave these results, these masks, to archaeologists and asked them to grade their quality. And we see that in the majority we are above 5, above 4 and 5, in a grade of 1 to 10. And more importantly, we could see that our masks in general improve the processing time. So it helps the professionals in the processing. You see, blue is without our mask, initial mask, and red. Blue is together with our masks when the archaeologists used our mask as initial guess, and red is without. So we can see that in most of the majority of time, blue is below the red, which means that it helps. Okay, the next project that we worked on is completely different, and it tried to look on a semantic perception of shapes by humans. So the idea here is to try to learn how humans perform abstraction, shape abstraction, and understand shapes. So we call these projects One Sketch, learning high-level shape features from simple sketches, and it's from last year. And our inspiration was one-line sketches. So we looked at these representations of shapes that are done simply by drawing one sketch, one line. The idea is that you cannot raise your pen from the paper or your pen from your pad, and you have to draw something meaningful. And when we looked at these human sketches, these are all made by human, we could see that they're quite complex, and they can convey a lot of information and a lot of complex ideas, like flowers growing in a vase, some kind of a woman dancing with a lot of motion, and some kind of poses, animals, etc., with very few and very simple sketches, very abstract. Still, we can understand as humans what's going on here. And the idea is to explore this kind of abstraction and shape representation with computational model, a deep learning model. Okay. So what we try to do is to look at how people draw one-line sketches quickly and very compact. And so the idea is to have some kind of shapes, as you can see here, and to look at their high-level compact representation made by human and try to learn what's going on here. So learning these representations is something that is quite challenging. It has to be coherent. So humans many times draw one shape very differently. You can see this car here. You can see three completely different representations. Same like the vase here, this lamp. You can see one human draw the top, one just the stick, the stand, and one maybe some kind of a curve that belongs to this headlamp, and so on. So it's a lot of variation, and we try to build a representation in using computational tools that it should be coherent, robust, and still convey the human statistics. So the paper that we wrote here and the research that we performed had several contributions. First of all, we created a data set. We are the first to build a benchmark that tries to summarize the variety of one sketches in a coherent, reliable way corresponding to shapes, to known shapes. Then we build a neural representation of the space of sketches, which we called an embedding space of the one sketches. And based on this, and you can see the embedding here. So this is a visualization, a 2D visualization of how the embedding of sketches looks like, how it was positioned in space. And this embedding, I will show you shortly, is very interesting because it allows us to really understand shape abstraction and to go to perform tasks like image retrieval from very simple sketches. So it gives us a very high-level semantic representation of the shape space. How did we perform this? So the idea was to create a benchmark of sketches. As you can see here, you have a lot of sketches that describe. You see the top row is the sketches that were made by humans, and this belongs to the red row. They belong to the shapes that you can see in the middle row, the red row. And the idea is that these sketches are not only describing a shape, because then we will miss the abstraction, but they should be minimal in terms that they should be sufficiently differentiating between the shape that they describe and another shape. So we have a correct shape, or the shape that it belongs to, and a contrastive shape. Okay? And by doing this differentiation between a shape and its pair, we were able to focus only on meaningful semantic features. So it's not that we want to draw the exact shape. We don't want to draw all the details. We just want to focus on features that separate between one shape and another. And the pairs are random. The shapes are from ShapeNet. And the idea came to us from a game, a very known game called Pictionary, where people try to sketch very quickly and very simple some ideas, sometimes quite complex ideas. And this game is very successful. It's called Pictionary, and very famous and well known. And people love to play it, and it's quite successful. And actually, it shows that people with very, very simple sketches can really convey quite complex ideas. And we did the same. So we build an interface. You can see the interface here, where we show people three shapes you can see here, and they should draw a minimal sketch, a minimal stroke that separates this shape from the other two. That was the task. And the sketch should be minimal. It should not have too many lines and too many details. So you can see here, for example, here, if the user draw too many details, it was canceled. And it should be also sufficient that it should separate. So here, for example, you can see it's not enough. They look almost the same. So we canceled the line to show this lamp. Here, the drawing was enough because it also has these angles. Right? So again, so the sketching should be minimal. Here, it's not minimal to separate this bicycle from the lamps. And here, it should also be sufficient. It should be separate. So here, this line was not sufficient because it didn't separate the two lamps. This one separated. So these are the two goals. Yes, minimal and sufficient. And then we also had the QA, where we did the symmetric task. We give the user a sketch that somebody draw, and we ask to guess this sketch to which of the three shapes it belongs. And this is a way to do QA, to do quality assurance. So we remove all the sketches that humans could not discover, could not distinguish, could not guess. So we look at all the sketches that receive more than 50% accuracy in the human task. Actually, our data was made quite good. We obtained 91% of the sketches that pass this quality rate. So we have a quite good data set. We also remove sketches that are too long or too detailed. So we ended up with a benchmark which holds something around 4,500 samples taken from 250 participants, each drawing average 8.8 sketches, and so on. And then after collecting this data, we moved to modeling the embedding space by using a triplet Siamese network. The triplet Siamese network has three main branches, one for the sketch and two for the other images. One is the positive image that the sketch belongs to, and one is the negative image which the sketch should separate. Okay, and the Siamese networks are simply encoders that try to encode the three images into an embedding space such that the sketch and the positive image are close, and the sketch and the negative image are far away in the distance of the embedding space. We use a triplet loss. The triplet loss simply measures the Euclidean distance between images, between the sketched image in the embedding space and the positive, and the sketched image in the embedding space and the negative. And this distance should be as big as possible. We try to maximize this distance. Then in the selection test, we're given two images and a sketch, and we simply take the maximal between the difference when image number 1 is positive and image number 2 is negative, or image number 1 is negative and image number 2 is positive in the branches. And we simply select the positive image that gives the highest of this term. Okay, so this is the result. Okay, we take a sketch, we take a pair of images, we feed it to the network, and we take the one pair that gives the maximal grade. So here, this is the middle row where we take, these are the images that maximize the loss, the triplet loss. We perform pre-training by training the image branches with ImageNet and the sketch branch with Sketchy, just to get features that belong to images and to sketches. We do augmentation by rotating, translating the sketches in order to allow some kind of some invariance to position. Okay, I will move away from these details. And then we can see that the embeddings gives quite interesting features. We see that by taking the 2048 dimension space to a visualization of 2-dimension, we can see that shapes are grouped semantically, not by similarity, by shape similarity, but rather by features. You can see, for example, in this cluster here, that the similarity is more about some roundness of shapes, some curved shapes, while the top cluster here, you can see they're more like 90 degrees angles, things that look like more CAD, furniture, weapons, and etc. You can see that actually it belongs to what the people sketched. So you can see if we take some clusters, you can see here a cluster from the space, the embedding space. You can see that here are all belonging to sketches that are circular. Here are sketches that look like more like line sketches, and so on. We can see that the accuracy of the differentiation is quite similar to what humans do. So if you take now a sketch and 2 images and you feed it to the network in the testing step, we get results that are similar to the 91% that humans do in our experiment. So actually, we sometimes got even higher, but maybe this is an outlier, but overall, we are in the same range as, so the model that guesses the right shape from a sketch among a triplet is quite as the peak of performance as humans. We also did some kind of robustness analysis by removing some part of the sketches, and we see that still the accuracy overall stayed high, meaning that compact sketches are quite expressive. They're good enough. So even if you cut 50% of a sketch, you still hold some information. So it means that we could also reduce more the task of writing sketches to get still a good embedding. We also applied the sketch paradigm to image retrieval, and we see that if we look at the number of sketches, so the color here are the number of sketches that we use. The more sketches you use to describe a shape, of course, you get better accuracy in the retrieval. Here, the K is the K top retrieved. So if we look at the K number 1 is just we try to be as accurate as the best retrieved shape. And if we are more tolerant, we allow 3 or 4 or 5 up to 10 best retrieved shape. Then we see that our model can give one of the 10. Always we will get a retrieval that is one of the best 10 shapes that we can retrieve compared to other shape-based image retrieval. Of course, that the model has limitations. When the sketch is not significant enough, here we draw something that is circular. So we have something circular also in this cup, but also in the bicycle. So sometimes it will not be sufficiently separating. Sometimes the features that somebody draw, the sketch was too high level, was too subtle. So it was like an outlier. For example, here is this X. It's a symbol on this remote. It does not have enough structural or geometrical information to be able to deal with. So it has to be something that it's relevant to the shape and not something that it's too high level. Okay, I still have maybe 5 minutes. I will show you one last work, totally different. So I'm trying to capture quite different ideas. Here, the work is called the PHY-DNet, Physical DNet++, which is an enhanced physically constrained long-term video prediction. It's from 2022. And the idea here was that we want to look at videos and disentangle the physical partial derivatives that govern the physical motion. Sometimes there is physical motion in some videos with the visual details. And if we have the parameters of the video or the physical, we can then predict a lot of phenomena in these videos. So we look here at some specific videos that involve ball collisions and gravity, and also flocking, like crowds that go and follow some biological and physical laws. And we try to learn these trajectories, this physical trajectory. Here you can see this is a crowd, and this is a crowd simulation. And we try to extract the physical laws, the partial derivatives that govern these kind of crowding systems. And we also added a novel relative flow loss, we call it RF loss, which accounts for similarity in the dynamics of the video. Here is another example of ball collisions and from a billiard game. So we allow, by having this neural network, to capture both the visual and the physical terms separately, and then to perform even video manipulation. We can also if we have the physical laws, we can also change the video. So we also some video manipulation. This is the neural network. It's based on an existing physical cell, which involves a Kalman filter on the partial derivatives that it tries to calculate. And this physical cell, again, it's not our contribution. It looks at the moment loss, some squared error, and some perceptual loss. And this is combined with an LSTM, convolutional LSTM, that tries to predict the next frame. So this is the disentanglement of the physical partial derivatives and the hidden states of the LSTM. The idea that helped us here was something that we used in order to measure the prediction of the next frame, and this is called the RF loss, okay, or relative flow loss. So standard optical flow loss looks at the trajectory of some objects in the video and tries to minimize the trajectory. So for example, here, it will look at this trajectory, the blue trajectory, and try to see how this blue trajectory is similar to the orange trajectory. In our loss, we said this is not enough because sometimes these trajectories can move far, far away and things can go really, really uncontrolled. So we try to create a loss between two frames, how one frame flows into another frame from at the same time. So this is a global similarity between the ground truth, this is G, and the predicted P. The idea is that if you look at the optical flow, then all these trajectories between the time times 3 and 2 will look the same. These are the blue arrows. But if we look at the what's happening in the video, it's very far away. You can see these trajectories are actually far away. So we try to look at a more local frame-to-frame similarity. And here you can see some results of collisions, bouncing balls, some motions, and some crowd simulation that we are able to predict. We get quite high accuracy compared to state-of-the-art. If we compare to, in an ablation study, comparing to networks that do not use our architecture and our losses, we can see that our model is much more consistent and less blurry, as you can see here and here. This is the comparison. This is our result compared to a result of a network without using our formulation. You can see our is much more concise. Same for crowds. This is ground truth. This is our result, and this is a similar result without our components. You can see you have a lot of blur here. Here also things behave quite weird. We can also manipulate the motion. This is the original, and we can create new trajectories. Here is again a manipulation. This is the ground truth, and here is our result. You can see we can really manipulate how the motion looks like. Okay, I will not go into the ablation study due to the lack of time. Okay, in terms of conclusions, this work has some pros, which is that we are able to control and manipulate videos and really get the physical terms. On the downside is that we were not able to boost this to more complex physical scenarios, and this is a question that needs to be answered later on. So I will stop here. Thank you very much for listening, and of course I'll be happy to have some questions in the time that is left.
Okay, thank you, Andrew Schaff. It is very interesting.
Thank
Please
you.
hold on. We will gather the questions from the audience. Any questions? Okay, I have a question. For
Sure.
glyphs with very limited data, do you think deep learning based methods is better than traditional methods?
For what? Sorry?
For the first work, it has very limited data. Do you think deep learning is better than traditional methods such as geometry based methods?
Yes. The answer is yes. Always. I think of course, if the problem is too limited, if you have only one example, or if you have only one, experiment, of course not. But for us as computer scientists, since all problems try to become larger and more general, and you want to move it from one domain to another, it's always better to have a deep learning model that has some kind of prior, or some kind of even if the data of the model is not exactly what we have, it can help because it will give you some features that can be then inserted in our problem. So I believe that the neural networks are really the Lego of these problems, and you can always build on top of others, and you can disconnect and connect. So it's really, I think, the best idea to go.
Okay, thank you. Due to
Sure.
the time constraints, we will conclude this talk. Thanks again for Professor Andrew Schaff.
Thank you, and nice being with you here. Thank you.
Thank you. The next speaker is Professor Peng Bobo from Harbin Institute of Technology, Weihai, China. Professor Peng Bobo is a professor at the School of Computer Science and Technology, Harbin Institute of Technology, Weihai. He obtained both his bachelor's and master's degree in computer science from Shandong University and his PhD in computer science from the University of Hong Kong. He completed postdoctoral research at the University of Hong Kong and the Visual Computing Center of KUST. His research interests include geometric modeling, computer graphics, and computer-aided design. He received the Garton Award in 2017 and the Best Paper Award at SMP 2020. His talk is entitled CNC Flag Milling of Freeform Surfaces with Customized Tools. Let's welcome Professor Peng Bobo. Professor, you should open your microphone.
Okay.
Okay.
Thank you, Professor Tang, for the introduction. Hello, everyone. It's my pleasure today to present our work at the AG webinar. The topic of my talk is about 5-axis CNC flank milling of freeform surfaces with customized tools. So we are talking about the industry component which contain freeform surfaces that are related to the functionality of the component. Here I show some examples. So this is a brick model, and this is the impeller model, and both have blade surfaces which are doubly curved surfaces. And our aim is to machine these surfaces with high precision. And our aim is to generate a machined surface that approximates the desired surface. And we use a technique called 5-axis CNC machining, which is a leading technology, manufacturing technology. It is a material removal process, and the machine has a five degrees of freedom, 3 for translation and 2 for rotation. And before conducting the real machining, a simulation stage is often necessary to validate the machining process. This includes checking for example, checking the collision between the cutting tool and the workpiece, and to measure the approximation error. And we should to ensure the motion of the cutting tool should be physically feasible, and the machine error should be under the tolerance. And in this talk, we discuss a specific CNC machining technology, which is the flank CNC machining. The flank CNC machining is it uses the side of the cutting tool to cut the material. So during the cutting, the cutting tool touch the material at a curve at any time instance. So this is more efficient than the traditional port milling, because port milling, during port milling, the cutting tool touches the material at a single point at a time at any instant. So you can see here, this is a flank milling of the blade surface. So in flank milling, the most commonly used cutting tool is like this one, the conical tool. The shape of the cutting tool is like a cone surface here. But the conical tool has a linear profile curve, which may be not suitable for machining the preform surfaces, which are often doubly curved. So in this talk, we will investigate the utilization of more general cutting tools, which may have a varying curvature. Here we can see some different cutting tools with a varying curvature. This one are cutting tools with which are assembled with cutter, and the bottom one, these are actually the grinding tools, which are used for grinding material. In order to make a mathematical modeling for the cutting tool, we can observe that the cutting tool, when it rotates at high speed about its tool axis, it is actually can be represented by a revolution surface, like this one. So in our discussion, we will use revolution surface to represent a cutting tool. So here is the problem we are going to solve. We are going to present a basic algorithm, which is the fitting of envelope of a surface of revolution. So the problem is like this one. So give a surface a revolution. It is for the cutting tool, and it can be subject to optimization. And we want to find its motion in the space. That is actually the motion of the two axes in space, which is actually a root surface. And we want the envelope surface of this motion to approximate a target. The target is the design surface to be machined. So this is a problem of envelope surface fitting, actually. So the objective is to obtain large patches, because large patches is more efficient in machining. So that is why we are using the flank milling, because flank milling the patch is large. And of course we also need to control the approximation error. And the flank milling has another advantage, that it's scallop free in its single patch. The scallop is the residual material left between two machining passes, like this one. This is the scallop. The scallop may degrade the smoothness of the surface, so it's not good. But if we use the flank milling, the scallop can be eliminated. And to maximize the degree of freedom, we will simultaneously optimize the tool shape and the motion path. The tool shape, as we have already said, it can be represented by a revolution surface. And the shape can be defined by a radial function, which is the radial is the radial of the sphere, because the revolution surface is actually the envelope surface of one parameter of spheres with the center hitting on the line of straight line. So the revolution surface can be represented by a radial function. And in the discrete form, it can be represented by a vector of radius. And for the motion path, we use the B-spline surface for its expression. And the degree is n by 1, because it's a motion of a two axes and actually a root surface. So we use the degree n by 1 B-spline surface for the root surface representation. And by optimizing the cutting tool, the shape of the cutting tool and the motion path of the cutting tool, we want to minimize the distance between the envelope surface and the desired surface. So the key functional term in the objective of optimization is a distance term. So it is used to define the approximation error. The approximation error between the envelope surface and the target surface is formulated using the motion path in this way. We can take some sample points on the ruling line, and then we compute the foot point on the target surface. And then the approximation error can be defined like this one. N is the normal vector at the foot point. So if we minimize this objective function, so the approximation error can be minimized. And in addition to the distance error, we also need some other terms. The first one is the fairness term. This term is used to define the stability of the motion, because we prefer a stable motion. That means the without big acceleration. So this function is defined for the fairness of the boundary curve of the root surface. And another one is the rigidity constraint, because the motion of the cutting tool is a rigid motion, which means the the two axes, the length of the two axes keep constant during the motion. So we use this two axes constant length constraint, this one. So the final objective function is the combination of these terms, and we minimize it with the Gauss-Newton optimization method. And here we show one simple example. For this example, we in order to show the capability of the optimization, we start with a poor initialization. You can see the motion path, the initial motion path is ugly, and the approximation error is very big. The color coding is a approximation error. And then we optimize the motion path and the cutting tool. You can see the approximation error become better and better. So because our optimization method is a local optimization, so the one most important issue here is the initialization. So this initialization includes the both the cutting tool and the motion passes. But this is a very challenging problem, and there are no existing methods for it. And here we discuss a simpler problem where the tool shape is given, and we investigate the initialization of the motion path. Clearly, the initialization of motion path depends on the tool shape. And here we discuss general tool shapes. As we have already mentioned, the tool shape is a revolution surface and can be represented by the radial function. Like this one, here is a radial function used to represent the revolution surface. So the RS is the radius of the sphere. And actually, given the radial function, we can also compute the profile curve of the revolution surface, which often called the meridian. So the equation is like this one. So the meridian can be computed using the radial function. And the radial function is very good to define the distance error, as we already seen. So for motion path initialization, our method first searches the space near the target surface for specific line segment. The distance field of the target surface along this line segment should match the radial function of the cutting tool. After identifying these line segments, we will organize them into sequences for motion path initialization. That is, we want to find some line segment near the target surface. For this purpose, we need to investigate the distance field of the target surface. Suppose the distance function d. And the distance given by the tool is this one, the radial function Rs. And we need to find the vector v along which the first and the second directional derivative of the distance field are equal to the corresponding derivative of the radial function of the tool. So this is the constraint. match the radial function of the cutting tool and the distance field of the target surface up to second order. So to address the distance field of the target surface, we formulate its second order approximation. Firstly, we explore the 2D case and obtain the second order approximation of the distance field using this function. And by observing the symmetry, we can then extend the function into 3D space. So this is the second order approximation to the distance field in 3D space. So now we have the second order matching constraint, and we also have the surface distance approximation. Then we can obtain the constraint like this one. So the V is the unknown variable we need to compute. And with the unity of the V vector, and combined with these two equations, and we're actually computing the intersection of the two quadrics and one unit sphere. And generally, there are 8 intersection points. But due to symmetry, actually, in general, we can compute 4 directions for space point. That means given a space point, we can compute 4 directions, which along these directions we can get the changing of the distance, which will match the shape varying of the cutting tool. So when we compute the direction vector for some point in space, we obtain a multi-valued vector field. And we aim to investigate this vector field to produce some straight line segment on which the distance field matches the radial function of the tool. Thus, this line segment can be used as the tool axis. The integration is done by starting with a point and move along one of its direction vector, a small step, to a new point, and then checking the direction vector of the new point. If there is a direction vector at this new point that is almost parallel to the current direction, then we can continue this process. And this process will stop when there are no parallel direction vectors available. And in this way, we can get an integration curve in space. And we will find the integration curves which are close to straight curves. And then we can fit the curve with a perfect straight line. The tool axis and the distance field along it define a cutting tool, which is a revolution surface. And we need the cutting tool to be able to move tangentially on the target surface, but which is not true for all the line segments we have already identified. To address this issue, we compute the tangential mobility of each tool. We take some sample points on the tool axis and compute the foot point on the target surface. So the tangential movement implies that the movement direction of the foot point should be orthogonal to the line connecting the sample point and the foot point. And this is equivalent to the orthogonality of the moment of the sample point, the moving direction of the sample point, and with the connection line, which is a white line. I mean, the tangential mobility should be defined by the orthogonality of the vector v and the direction of the along the white line. Therefore, we can define a minimization problem, and we solve this minimization problem, and we can get a movement vector for the sample point. And the value of this function can be used as an evaluation of the mobility of the cutting tool. That is, a small value of this function f indicates better tangential mobility. Now let's see the number of variables in the moment vector. The variables in the moment vector have 5 degrees of freedom, because each endpoint of the two axes has 3 degrees of freedom in space. And due to rigid motion, 5 degrees of freedom remain. And the moment vector of a point inside the two axes is a linear combination of these 5 degrees of freedom. Now we present an example. Here the target surface is an exact envelope surface of a moving tool. We begin with an accurate starting revolution surface, and we compute the tangential moment of the cutting tool. And then we move the tool along the computed direction and repeat this process. And we observe that we can get the family of cutting tools along a motion path. And here we show the approximation error. So this, we can see this error is small. This is not by optimization, this only by the computed tangential moment. So this error is small enough. However, even after we remove the line segments that do not exhibit good tangential moment, the remaining line segments are still numerous. We simplify these lines by employing a line clustering process. And the line distance is defined by this equation, which measures the distance of the midpoint. M is the middle point, and the direction vector, V, the distance between the projection direction. And we do the clustering by a simple k-means clustering algorithm. And here we show an example of a line clustering. The initial number of lines is about 8,000, and after line clustering, we can get 500 lines. So the next step is to organize the line segments into sequences. And for this, we need to define the closeness of a line segment. We use a method based on a segmentation of the target surface. Here we use a VSA segmentation for the target surface. And the closeness between the segmentation can be used to define the closeness of the line segment in space. And then by organizing the line sequences into some code mesh, then we can define the initial piecewise surfaces for the motion passes, which are then can be optimized further to reduce the approximation error. And here we show some experimental results. You can see 3 different shapes of the cutting tools. And this is the motion passes for various cutting tools. The color coding is the approximation error. Here we show the coverage by a family of the motion passes computed using our method for various cutting tool shapes. So this is an example for the convex surface. Convex surface, we can see the cutting tool, the shape of the cutting tool is concave. So it's adaptive in order to adapt to the target surface. And this is an example using an on-market conical tool. So this one, and this here are the results using our algorithm, the motion passes. That's the color coding is the approximation error. And this is a comparison with the result using the Siemens NX software. Actually, we can obtain smaller approximation error and a better surface quality. You can see the surface is smooth. And this is an example using a customized cutting tool to machine this surface, a blade surface, this one. And we will compute and optimize the cutting tool, and then we manufacture this cutting tool. So the manufacture of the cutting tool has two steps. The first step is to manufacture the tool core, like this one. Actually, the shape is close to a conical tool, but it's not a conical tool. And the second step is to cover the surface of the tool core with some abrasive grains, which are actually some diamond particles. So this is the manufacture of the cutting tool. So this now we show the real machining process for this product. So this is the roughing operation. So in this stage, we use the traditional method. We use the result by the Siemens NX software. So this is the initial roughing, the result by the roughing operation. And during the semi-finishing stage, we also use the traditional method, and this is the result. And in the final finishing stage, we compare our result with the result by NX software. So the left one is the result by NX software. The right one is the result by our method. We can see the obvious difference between the surface. The surface smoothness is different. So now we do some examination. So here is the dimensional deviation exam. You can see the deviation by our method is smaller. It's actually under 48 μm, which is good enough for application. And this is the roughness measurements. So the left one is the result by the traditional method, and the right one is by our method. We can see the roughness by our method is much smaller than the result by the traditional method. So this is about 6.21 μm, and our result is about 2.67 μm. So now we extend our method to machine learning technology, which is called tricorder milling. Tricorder milling. This is also a flux milling technology, since it also uses the tool side for cutting the material. The tricorder milling, here we show the traditional 2D milling, the 2D tricorder milling. So the two passes of tricorder milling can be decomposed into two components. One component is called the active part, and another one is the back half part. The active part is the front half part. It will during this part, the cutting tool touches the material, it cuts the material. But in the back half part, the cutting tool does not touch the material. So actually, the path is a sequence of cycles like this one. This one. So the benefit of this technology is the following. So the tool wear can be reduced by this technology because the heat is dissipated in the back half passes. So the lifespan of the cutting tool can be extended. This is why the TR milling is widely used for cutting very hard material. And in this talk, we will give an algorithm for tricorder milling of 3D cavities, which means a cavity bounded by freeform surfaces in space. We need to decide the motion passes and also the shape of the cutting tool. So here we can see the both sides of the cavity are called the side surfaces. And we need to ensure a high precision milling to the side surfaces. So the key is we need to compute the tool shape adaptive to the target surface and the TR path planning.
Okay, Professor Bo, you can just reshare your screen.
I should start with from which slide?
You can just continue and reshare the slides.
I should start with this slide.
Okay.
Okay, here we in this slide we see the last one. So here we are talking about the initialization of the optimization. So the initialization should include both the cutting tool and the motion path, but this is a very difficult problem, and here we discuss the problem with a given cutting tool and the only initialize the motion passes. And the cutting tool is represented by a radial function, the RS. And we want to find some line segment in space, such that the distance field along the line segment should match the radial function of the cutting tool. And this amount to solve this constraint. It is the distance. We should find some vector along which the distance field, the first the direction derivative of the distance field should match the radial function of the cutting tool up to second order. And for this purpose, we need to give a formulation for the distance field. And here we give a second order approximation to the distance field, like this one. This is a formulation in 3D space, and this is the formulation in 2D space. So now we have the second order matching constraint and the surface distance approximation, and we can obtain this constraint, and we will solve this constraint to for the vector v, which are v1, v2, and v3. And because the v vector is a unit vector, so it is actually a unit sphere in space, and these two equations are quadratic surfaces. So we actually need to solve the intersection between two quadratic surfaces and one unit sphere. And there are in general there are 8 intersection points. But due to symmetry, we can find 4 directions for each space point. And then after we compute the directional vector for many sample points in space, we are actually we will obtain a multi-valued vector field, and we want to integrate the vector field to obtain some straight lines in space. And we do this by starting from points and go along one of its direction vector to another point, and then we compute we check the direction vector of the new point. If the direction vector is almost parallel to the current direction, then we go further and further until the direction vector is no longer parallel to the current direction. And in this way, we can get some integration curve in space, and we will find some integration curve which are close to straight one, and then we compute the perfect straight line fitting to the curve. And then we will check the mobility of the line by solving a minimization problem. So this is the evaluation of the mobility, tangential mobility of the line segment in space. So we minimize this function, and we get the motion vector v for the summon point on the 2 axes. And this the function value can be used as an evaluation for the tangential mobility of the line segment, which means if the value is small, then the function the value is small, then the mobility tangential mobility of the line segment is good. And the motion vector has 5 degrees of freedom because each endpoint has 3 degrees of freedom, and due to the rigid motion, 5 degrees of freedom remain. And under the motion vector for inside point is a simple linear combination of the 5 degrees of freedom in space. And here is an example. We compute the motion of a revolution surface and get a sequence of position. And we can compute the envelope surface and measure the approximation error. You can see here the error is small enough. And then, because even after we remove the lines which does not have good tangential mobility, the number of the lines is still very huge. And then we do a line clustering process, and the distance between the lines are defined like this one. And then we do the clustering by K-means clustering algorithm. You can see that by this line clustering process, the number of lines can be greatly reduced from 8,000 to 500. And the next step is to organize the lines into line sequences, like this one. And the line sequences can be used as a control polygon to define the piecewise surfaces for the motion passes. And for this purpose, we need to define the closeness between the line segments, for which we use the segmentation of the target surface. And here we show some examples. We can see for various shapes of cutting tools and the computed motion passes and the approximation error, they are good enough for application. And here we show the coverage by the motion passes. And here we show an example with the conical tool and a comparison with the result by the Siemens NX software. We can see that the approximation error by our method is smaller than the result by the NX software, and the surface quality is also better. And here we show an example of a customized cutting tool, and the blade surface is this model. We will compute the shape of the cutting tool with our algorithm, and we manufacture the cutting tool. Firstly, we manufacture the tool core of the tool, the tool core like this one. And then we will cover the surface with some diamond particle to make a abrasive grain on the surface. And here we show the manufacturing process. Firstly, this is the wrapping operation. This is the semi-finishing. In this two stage, we use the traditional method, and in the finishing stage, we use our method, this one, and a comparison with the traditional method. We can see the surface smoothness obviously are very different. And here is the dimensional deviation examination. We can see the dimensional dimensions by our method is much smaller. It's actually under 45 μm, which is a good enough for application. And this is the roughness measurement. But the left one is the result by the traditional method, and the right one is the result by our method. We can see the roughness by our method is much smaller. And then we'll talk about the TR milling, Chugordo milling, which is actually the motion path in Chugordo milling is a sequence of cycles, and each cycle has a front path and a back path. And in the front path, the cutting tool will touch the material, and in the back path, the cutting tool does not touch the material. So So this technique has the benefit that the tool wear can be reduced because in the back pass, the heat is dissipated. So and the lifespan of the cutting tool can be extended. That is why the TR milling is widely used for cutting very hard material. And here we will give a present an algorithm to TR milling 3D cavities bounded by freeform surfaces. We can see here is an example. The space between two blade surfaces is the 3D cavity, and the side surfaces are the S1 and S2. We need to ensure a high precision milling to the side surfaces. And we need to compute the tool shape adaptive to the target surface and compute the TR path planning. We need to minimize the error, and in this work, we also consider the material mole rate, MRR, and the CWE. The MRR should be maximized, but the CWE should be a constraint under tolerance. And the algorithm has three stages. In the first stage, we compute the flank milling to the side surfaces, and we get two side passes, left one and the right one. And in the second stage, we compute all front half passes consequentially, the one by one. And in the third stage, we compute all back half passes, and finally we get the whole TR milling path. For the motion path, we also use the bits by surface, with the degree n by 1 bits by surface. And we solve a similar problem as we have already discussed in previous slides. That is, we minimize the distance error and together with the fairness of the motion path and the rigidity constraint. But the difference here is that we need to control the overcutting. The overcutting is controlled by using a virtual surface like this one. And here the parameter alpha is used to control the overcutting. Another difference is for both sides, we should use the same cutting tool. That is the vector of a sphere radius will be the same for both sides. And after we compute the side passes, the next step is to compute the front half passes, which is also represented by a bitspline root surface. And to ensure the high precision to the side surfaces, we should use two constraints. The first one is the G0 constraint, which means the ruling of the passes should be lying on the side passes. And this can be formulated using the bitspline control point. The second constraint is the G1 constraint, which means the motion of the motion direction of the point on the end ruling line should be parallel to the motion direction on the side passes. So this is actually a tangential constraint, and which can be also formulated using the bitspline control point, because this is due to the nice property of the bitspline curves, bitspline surfaces using the clapped Knox vector. And in this process, we consider the material mole rate, which is defined like this one. Here, the V is the space removed by the front half pass, which is actually the space enclosed by two envelope surfaces. And L is the length of the motion path, which is actually is used to measure the time. And we also consider the cutter workpiece engagement, which the CWE is actually the touching surface between the cutting tool and the workpiece. So it can be approximated by a family by a sequence of circles, and the CWE can be approximately defined by the maximal engagement angle. Engagement angle is the angle, this angle. So we can have the we can define the problem like this one. We maximize the material removal rate subject to precision constraint and the CWE constraint. And the algorithm depends on a path optimization, which is a sub-algorithm which computes a root surface, assuming the G0 and G1 constraint about the end control point, which actually is similar to the path optimization in previous slide. And then we compute the front half passes using a two-stage method. The computation is one by one. So we firstly we compute the first half pass, and then we assume the first pass is fixed, and we compute the next one. In the initialization stage, we move forward the end rulings on the set passes until the CWE is violated. And then when the CWE condition is violated, we need to move back the motion path. But directly controlling the motion path is difficult. So we control the envelope surface. So we'll move back the points on the envelope surface where the CWE condition is violated. And then we compute the path, the motion path using the path optimization algorithm. And then we iterate between these two operations until the CWE condition is satisfied. And finally, we compute all the back half passes. This is much simpler than the computation of the front half passes because the cutting tool does not touch the material. And for the some deep cavities, we need multi-layer passes because one layer is insufficient to obtain a good machining quality. For multi-layer computation, it also has two stages. In the side part computation, the computation is similar. The only difference here is the same vector of 2 radial is used for all layers. That means we use the same cutting tool for all layers. And in the TR part computation stage, the computation is the same actually. And we start from the top layer and process the remaining one by one. Of course, we need initialization of the motion passes. And finally, I show some examples. So this one is a one layer example. You can see before optimization, the error is 2.1, and after optimization is 0.08, which is much smaller. Here we see the engagement angle optimization. You can see that after optimization can be controlled under the tolerance. The tolerance we use 60 degrees. And this is a comparison with a conical tool example. You can see using the conical tool, the error is big, but using our method, our customized cutting tool, the error is much smaller. This is a comparison with on-market barrier tool. The tool is like this one. This is the definition of this tool. We use our customized cutting tool. The error is 0.08. but using this more market barrier tool, the error is 0.5, like this one. So our error is much smaller. So this is a multi-layer example. So this is using 3-layer, and the bottom shows the result using a single layer. So we compare the approximation error. We can see using 3 layers, the approximation error is much smaller. So this shows the engagement angle and the material more rate. So this is another multi-layer example. We use 5 layers. So this is a comparison of the 5 layer with the 1 layer. Okay, this is my talk. Thank you very much.
Okay, thank you, Professor Pombobo, for the interesting talk. Any questions? Okay, I have a question.
Okay.
Since current milling machine tools always use the rigid mechanism robot arms, some of my friends are conducting research about soft robotics. If in the future soft robot arms are used for this type of task, how do you think the modeling should be done?
You mean the soft robot?
Yeah.
The modeling of the soft robot.
Yeah. We can use soft robot arms to conduct the milling task.
To conduct the motion path, right? The motion path of the cutting tool.
Yeah.
Yeah, the robot it has a more degrees of freedom, I think. So it's more flexible than the current than the CNC machine. I think so. So the motion path of a robot is I think it's more complicated than the problem I'm talking here.
Okay, thank you. Due to the time constraints, we will conclude this talk. Thanks again, Professor Pombobo.
Thank you.
Thank you. Bye.
Bye bye.